Hello, wonderful people. Welcome to Cosmology Talks. Today we have Min Nguyen, who is a Lineweaver Fellow at the University of Michigan, and Beatrice Tucci, who is a PhD student at the Max Planck Institute. They're talking today about field-level inference, which is where one uses the density field itself or its Fourier modes to construct the likelihood. This is as opposed to using summary statistics like the power spectrum or bispectrum, or even more exotic things like voids or halo mass functions. In this talk, their results are ultimately comparing what cosmological constraints are possible with field-level inference to what would be obtained with a best case, more typical analysis using a power spectrum and bispectrum. I love the idea of field-level inference because it is in principle the actual thing we want to do. If we've measured the density field, why compress the information inside of it into a new statistic like a power spectrum and not just use the field itself? Of course, when the field is linear, the power spectrum has all the information. So historically for the CMB and very large scales for galaxy correlations, this has been fine. And I guess any more sophisticated field level stuff would have just rediscovered the same results. But as we try to probe quasi-linear or even fully nonlinear scales, if we stick to summary statistics, we're inevitably throwing information away. Whereas, in principle, with field-level inference, we don't need to. So that's very exciting. Of course, field-level inference is therefore more difficult to do, but this hasn't stopped Bia and Min and shouldn't stop the community. So welcome, Bia and Min. Do you want to start by telling us briefly about your paper?
Thank you, Sean, and thank you for having me today again, and thank you for having us. So, as viewers of this channel already know, we're all very excited about ongoing and upcoming galaxy spectroscopic surveys. Typically, in these surveys, we record the galaxy position in three-dimensional space, but instead, when we analyze the data, we summarize the galaxy data into some summary statistics. And in this paper, the questions we try to answer is how much information exists and can be extracted robustly in galaxy clustering data at the field level beyond the summary statistics. In order to perform such a comparison, we have to take care to set up an apple-to-apple comparison. And so we need a forward model framework in which we can start from some cosmological model and initial conditions, forward evolve to generate a model prediction for the observed galaxy field, which we can then compare directly to the data, or we can compute some summary statistics for the inference framework.
So for the summary statistics case, we compress the same density field from the same forge model to the power spectrum and bispectrum, or the 2-point and 3-point correlation function of galaxies. And to obtain the posterior of the cosmological parameters, we do simulation-based inference.
Thanks. So if people are thinking of this talk or your paper 6 months or a year from now, and there's only two things they're able to remember, what would you want those two things to be?
Okay, so the first thing is that we actually provide an apple-to-apple comparison of field-level Bayesian inference and simulation-based inference with summary statistics. And as you can see in this diagram, we start from the same parameters and we produce the galaxy density field using exactly the same forward model. And then, of course, we do either field-level inference or we compress it further to summary statistics to do the analysis with simulation-based inference. And besides of using the exactly same forward model, we also use exactly the same observed data. So this is really a fair comparison between both inference methods.
Yeah. And is there any kind of conclusion about how much better field level inference is compared to summary statistics or things that you want people to take away? Or
Right. So I think in this diagram and these plots, you can look at the posterior constraints on the sigma 8, the amplitude of matter fluctuations. Specifically, we show the results as the ratio of sigma 8 over the true sigma 8 of these simulations. So 1 means an unbiased inference. And then blue is the field level, results from field level statistics. And then yellow is results from the summary statistic power spectrum plus bispectrum. In these two plots are results for two different tracer samples, two halo samples from two completely different simulations. And the top is for the analysis cutoff scale of 0.1 H over megaparsec, and the bottom are for the analysis cutoff scale of 0.12. Even at these very modest cutoff scales, you can see there's a big improvement factor between field level inference and power spectrum plus bispectrum as indicated by the numbers on the top right corners. The two posteriors in all cases are completely consistent, indicating that both the forward model and the inference framework is robust, and we can trust the improvement factor. So the conclusion is there's a lot of reliable information in the galaxy clustering at the field level, even after we correctly marginalize over all the physically possible galaxy formation models. in the sense of the effective field theory framework for galaxy formation and galaxy bias, which we will describe later.
Here you're looking at simulations and saying that in these simulations, and I'm sure you'll get into exactly what simulations eventually, but what kind of real world observational survey broadly should we be thinking about when looking at these plots? Is this a DESI equivalent plot? Is this a futuristic beyond DESI equivalent plot?
Right. Yeah, that's a very good question. So the volume of these simulations, I think, are roughly similar to the effective volume of the luminous red galaxy samples in the DESI year 1 data. And of course, with year 3 and year 5 DESI data, the number density will increase. So we are looking at the numbers, I would say roughly for DESI year 1 data or BOSS data.
Awesome. So let's get into the motivation and the background. You've gone into this a little bit, but let's go into more details now about what unsolved questions you wanted to solve and why were they still unsolved at this point of time and what makes this relevant today.
We know that the 3D distribution of galaxies in the sky can contain a lot of information on cosmology and can help us probably answering some of the open questions in physics. And one of the big questions is how can we actually extract this cosmological information from the 3D distribution of galaxies in the sky. And the way that people usually do that is to compress the galaxy density field into summary statistics, for example, the 2-point correlation function of galaxies, or its Fourier transform, the power spectrum, and the 3-point correlation function of galaxies, or its Fourier transform, the bispectrum. And another straightforward question actually is why don't we use directly the galaxy density field to do cosmological inference? And by doing that, we are not compressing the information and we are taking everything at once. And here in this case, our observable is the galaxy density field. That means that we basically count galaxies and put them in a grid. And this is going to be our 3D data vector. And the question we are trying to answer is when going from summary statistics to the field level, when we are taking the entire information instead of compressing them to summary statistics, how much reliable information can we gain on cosmology?
Why was this done in 2024 and not before? The most important reason, I believe, is prior to this Left field framework that we're going to introduce, there was no rigorous framework to model galaxy clustering at the field level. And by that, I mean other empirical or machine learning based or just empirical models basically do not take into account only small scale physics that can contaminate or bias your inference. Instead, in this effective field theory framework that Left field is based on, we have a rigorous cutoff scale where we say that or we admit that we are agnostic on the small scale physics, which we then marginalize over in order to produce a robust model prediction, theory prediction for the data on large scale or quasi-linear scales. And another challenge is even with a rigorous theory framework, you still need a numerical framework, a numerical program that is so efficient that you can now explore the entire parameter space that consists not only just cosmological parameters or a few Fourier bins in the case of summary statistics, but now remember that we have to explore all the Fourier modes in the entire three-dimensional data. So that typically goes to up to like 10 to the 6 parameters.
Awesome. Let's get into the details then. What have you specifically done in this paper and how do you end up with those lovely plots you showed earlier of the relative constraining power on sigma 8 at the end?
So in this beautiful cartoon by Jesse Muir from Perimeter Institute, you can see like over cosmic time why dark energy that we are very excited about, given the recent results, driving the expansion of the universe. Gravity also acts to pull matter and galaxies together and enhance the initial density fluctuations so that it grows over time. So one can quantify the growth of structure over cosmic time by a quantity known as amplitude of structure growth or amplitude of matter fluctuations, which is named sigma 8. It is basically the variance or the standard deviation of matter fluctuations in spheres of roughly 8 megaparsec over 8. And that will be our target for today. It will be our main metric to quantify the information content beyond low-order endpoints function, specifically 2 and 3 points functions. Why do we pay so much attention to get the case of galaxy clustering? That is because recently in cosmology, we have a a tension known as the S8 or sigma 8 tension, which is a tension arguably between probes of the early universe and late universe, in which the measurements or extrapolation rather of the sigma 8 quantity do not agree. However, these probes also typically probe very different scales, where the early universe probes tend to probe the large scales, the late universe probe tend to probe and are affected by the small scale physics. So to disentangle between possibility of new and late time physics or small and large scale physics, galaxy clustering is a perfect candidate because galaxy clustering probes typically late universe but on large to quasi-linear scales. And that is why we are after this target. But there's only one complication, that is galaxy bias. And by that, I mean the response of galaxy formation to long wavelength fluctuations. In this very simple toy model that I'm showing here, we have two fluctuations, one long wavelength in red and one short wavelength in blue. Let's assume now that we have a simple galaxy formation model in which galaxy only forms whenever the density fluctuations are above a threshold, which is in pink here. So with this very simple picture, you will see that we tend to form more galaxies at the region where the long wavelength is enhanced, and then we form also less galaxies at the region where the long wavelength is underdense. So in summary, this is a known unknown from the astrophysics of galaxy formation process. This known unknown can spoil our constraints from galaxy clustering simply because we want to measure the sigma 8, the amplitude of matter fluctuations, but we can only observe galaxies. So this known unknown introduces a perfect jersey between the galaxy bias, B delta, that I'm showing here, and the amplitude of matter fluctuations that is inside the linear matter power spectrum on the right also. In summary, we don't know whether when we observe a certain sample of galaxies, we don't know if we measure a sample with higher galaxy bias or we're actually measuring a universe with a higher amplitude of growth obstruction.
So Min so far has been talking about the linear bias, and we know that actually to make the connection between this distribution of any cosmological tracer that we observe in the sky, for example, galaxies, quasars, and so on, to the actual matter distribution, we have to write a bias expansion that we call. And in this picture of galaxy formation, what we know is that galaxy formation happens in small spatial scales and very long time scales. And this allows us to actually write this bias expansion as a function of the so-called operators, which are basically, you can write them as anything that can influence galaxy formation. And how you can actually do that is just to take all the allowed operators by equivalence principle, and you can write this extension as each order in perturbation theory, so that you have a set of bias parameters that you have to, at the end, marginalize over to obtain your, for example, posterior over the cosmological parameters.
And the idea is that in principle, these bias parameters could be modeling everything from baryonic feedback to the linear bias that Min just mentioned to complicated nonlinear structure formation effects. And it's just because there's certain symmetries the universe satisfies, the isotropy and, as you said, equivalence principle, that there's certain terms that are allowed here, and then you're able to kind of write them down and then treat them as constrainable parameters. Is that right?
Exactly that. We basically assume our ignorance about galaxy formation, and we are in principle integrating over all the reasonable process of galaxy formation, so that at the end we have these three parameters, which are the bias parameters. And we know that, as we said, galaxy formation can only depend on operators allowed by equivalence principle. And when we are marginalizing over these bias parameters, in essence, we are marginalizing over all the reasonable galaxy formation, feedback processes, anything you can imagine that happens on the small scales.
So that's a perfect explanation. I just want to quickly add something about the cartoon that we have here, because that answers your question about, for example, baryonic feedback. So the cartoon shows, the galaxy formation process over the entire cosmic time. So you can see that galaxy formation, even though they span the entire cosmic time, which is a very long time scale, right? We happen to live in a universe dominated by cold dark matter. So the actual region that is physically relevant to galaxy formation is actually very small. And so that includes only barometric feedback or any HEN, supernova that you can imagine. And so the EFT framework restricts the galaxy bias expansion and description to the quasi-linear scale such that we can safely modularize over these small-scale fluctuations or small-scale physics. So such description is expected to only valid, of course, above a certain scale. And these scales are directly linked to the scale where barometric feedback can become important or significant. This is, again, the diagram that we showed earlier. I just want to walk you through how we forward model the entire three-dimensional galaxy fields. So again, we start from a cosmological model or a set of cosmological parameters and specific realization of the initial conditions. Then we use Lab fields, this Lagrangian EFT framework, to forward model from that to the observed galaxy field, or to the prediction for the observed galaxy field. Now we compare that directly to the data using our likelihood, and then we repeat the process multiple times, basically doing an MCMC sampling for the inference to get the posterior. And in the blue box below, you can see our full posterior, where we have the Gaussian prior on the initial conditions as hat, and we're modularizing over all of the plausible initial conditions that are allowed by the data. The likelihood, the explicit FBI likelihood, is just a Gaussian likelihood that we're going to show again later. And then finally, we have the priors on the cosmological parameters, alpha in this case, BO, the galaxy bias parameters, and some stochastic noise for galaxy bias sigma epsilon that Bear already introduced.
When you have your likelihood over all of the Fourier modes, are you saying that likelihood of Fourier mode 1 is multiplied by likelihood of Fourier mode 2 is multiplied by likelihood of Fourier mode 3, et cetera, all the way down through however enormous number of Fourier modes you have? Or is there a likelihood kind of function of all of them so that it's actually likelihood of Fourier mode 1 being this and Fourier mode 2 being that and Fourier mode 3 being that? So it's not just a multiple of all of them. It's like a conditional probability of mode 1 given mode 2, et cetera, et cetera, et cetera. Which one of them does it end up being?
I think what you are trying to get at is the covariance, right? So the covariance between these Fourier modes. And in our framework, we have a covariance that is diagonal. It is basically because we don't describe the data in real space, but we rather describe the data in Fourier space. And then in Fourier space, beyond homogeneity, you can also assume isotropy. And so your covariance will also be, again, a diagonal.
Is it definitely known that it is a Gaussian likelihood, or is that something you've been able to empirically show? Or
right, that's a very good question. So this took us a while, but this was shown that the likelihood is expected to be Gaussian if you implement it consistently in an EFT framework. So there are certain operations that you have to do, but after those operations and at a certain scale, this likelihood is expected or shown to be Gaussian.
And when you say shown, is it in the paper we're discussing, or is there a reference otherwise where?
No, but you will find all the references in that paper.
You told me, and I believe you, that the Fourier modes themselves, the actual wave vector modes, not the amplitude at a given scale, but the delta K mode, are uncorrelated because of isotropy. This raises a confusion in me because we talk about things like the bispectrum when we've got this triangle of 3 Fourier modes, and after structure formation, that's non-zero, and neither is the trispectrum or the, quad spectrum, whatever comes after the trispectrum. Is it reasonable for me to have this confusion? And is there a way for you to explain why both of those things can be true?
So I would say the Fourier modes, the density fields or the galaxy fields, the Fourier modes are actually correlated. However, what is uncorrelated or what allows us to have a diagonal covariance is the errors in the prediction. So the difference between our prediction and the data.
What you've done now is completely alleviate my confusion about how these two things can be true. But I guess now I just have to take at face value your claim that the error in the prediction is uncorrelated. Is there a way to neatly show that or explain that?
This is up to leading order. Of course, there will be At the next order, there will be corrections that spoil this. And then you will need, for example, likelihoods in real space, or you will need some kind of hybrid likelihoods. But after leading order, this is correct.
And so your likelihood is the probability, the kind of Gaussian function, the e to the minus x squared. That x is the difference between the model parameter and the measured parameter, not the probability that that measured parameter could be there given a model of inflation or given some sort of initial condition model. It's actually that deviation. So
yeah, so the likelihood is what Bay is showing.
Okay, so now I have another question that might be answered later on, but you measure the data and it has a bunch of delta Ks and you use this likelihood. Let's say I have two inflationary modelers in the room, one who prefers model A, one who prefers model B. Can you tell me in an intuitive way where the information's coming from that model A person can say, ha ha ha, my model is better than your model in all of this?
Yeah, I guess my video or animation my partially answers that questions. But basically, if your model A and B can distinguish between the structure formation at a specific location, for example, at the locations of the clusters or at the location of voids, then this approach will tell you exactly that. So in this animation, on the top row is basically the data, two-dimensional slices through the 3D data, of course. And then at the bottom row is exactly the same slices through the model prediction. So as you can see, the likelihoods will tell you if your data has a cluster at that specific location, the likelihoods will identify and tells you the same configuration of initial conditions that give you a cluster at that location. And same for voice or any other statistics in principle. So if you think of using, cluster or void as your tracer instead of galaxies, because there have been claims, for example, saying that with voice you can access, higher order information beyond 2-point functions, for example. So then this approach will tell you exactly at that location you expect void and the size of the void.
Okay. When you marginalize over the initial conditions, you need a prior for those initial conditions. What prior are you using for the initial conditions?
Yeah, so we use a Gaussian prior for the initial conditions, and this is actually exactly why we need to start from the initial conditions. Usually, when you hear about field level inference, you also hear it's associated to forward modeling, and oftentimes that's why people associate the two as the same thing, but they're actually not. However, they typically go together because when you perform field level inference, as any other Bayesian inference, you need a prior on the additional parameters, in this case, the density field. So if you perform your inference on the evolved density field, then you have a problem of coming up with a prior that correctly describes the evolved density fields with all of these high order correlations that you have been worrying about. So if we instead start from the initial conditions, we know from, for example, CMB observations that these are very close to Gaussian, right? So we can use a Gaussian prior as a trick, and then together with the forward model, we can then perform the inference with these Gaussian priors. The price to pay is basically each sample is a simulation because you have to start from the initial conditions.
I think this is then honed in on exactly my confusion. If you've got inflation model A and inflation model B, this Gaussian prior will be slightly different, right? Because one will have a different spectral index, so you'll have a different amplitude of fluctuations at different scales. So then it's at this point of your pipeline that the different inflation models would do something slightly different, and therefore your final inference would be slightly different.
Right, exactly. Although in this paper I have to say that we restricted to Gaussian prior, and we only infer sigma 8, which is just a scaling amplitude, which is just a scaling parameter, right? But exactly like you said, if you have inflationary model A and B, then you have to modify this initial condition and the prior on the initial conditions. And then you just have to let gravity text over and then trust your forward model to correctly forward evolve these initial conditions.
But when you say a Gaussian prior, there's still one parameter in a Gaussian, right? The width. How do you pick that?
Again, that's a very good question. So for our case, we can basically parameterize the Gaussian prior just as a unit normal distribution. So it's basically has a variance of 1. because then you, for any given cosmology, you can use the linear matter power spectrum to scale up this unit normal distribution.
Okay, so you're not assuming a spectral index kind of primordial power spectrum of an amplitude with one spectral index kind of thing. It could have.
Oh yeah, we do, but we fix that. Right, so that goes into the linear matter power spectrum that I just said. So all the cosmology is fully specified by the linear matter power spectrum plus in our case the sigma 8 parameter that we vary, the scaling parameter.
But the matter power spectrum is calculated assuming an amplitude and spectral index initial condition. So if I had a funky inflation model that had a large running, you would have to redo this but allow for that variation of your initial conditions.
Yeah, so you would modify the linear matter power spectrum in that case. And then if you have primordial non-Gaussianity, then you have to modify also the prior on S hat.
Yeah, I didn't want to bring up primordial non-Gaussianity because it feels like it would break everything here, right? Because at this point you're assuming a Gaussian prior, and if I want to be able to actually detect primordial non-Gaussianity, I can't use a Gaussian prior for my initial conditions, right?
I think the beautiful thing is that in the forward modeling view, you just change the initial conditions, for example, to include any of your favorite inflation model, and then you just forward evolve it with the same model, basically.
Mm-hmm. But then when you're marginalizing over those initial conditions, you can't use a Gaussian likelihood, right? Because
you mean Gaussian prior, right?
Yeah. Sorry, yes. You can't use a Gaussian prior.
Right. So in that case, I would expect you to give me the prediction for the prior to use, right? Because from such an inflationary model, you should know what prior I should use, for example. Yeah. Right. So for the field level inference part, again, we have a Gaussian likelihood on the data. So this Gaussian likelihood basically will compare the data and the model prediction mode by mode for the Fourier mode. And again, we have here in this animation, I'm showing on the top row the two-dimensional slices through the data, and then on the bottom row, two-dimensional slices through the model prediction, the same slices, top and bottom. So you can see that as the inference machine runs over all the possible initial conditions, it starts to identify the initial conditions that correspond or can produce prediction that match the data. And so as the framework matches produce predictions that match the data better and better, you can see the likelihood is increasing in this case. One more thing you might notice when you watch this animation at slower speed or over again, you can see that the high density regions are very quickly identified, and it takes longer time for the inference machine just to fit the voice or the underdense regions. This is expected because you typically have you expect the high signal to noise regions to be identified first, and then the low signal to noise regions, and then you also expect to have more possibilities for these low signal to noise regions.
Cool. And then once you've got this set of initial conditions which are giving you the high likelihood, and set of cosmological parameters that are giving you the high likelihood, if you're an inflationary theorist, you can say, okay, does my inflation model like this set of initial conditions or not? And if it does like it, woohoo, I'm in business. And if it doesn't like it,
yeah, I think that's just reasonable to say. One thing I would like to add is that we jointly sample both the initial conditions or the density configurations and the cosmological parameters. So why I'm only showing here, the density fields, the cosmological parameter can also be, and the bias parameter as well, are also being sampled simultaneously. This is not like a sequential process, but this is like happens simultaneously. Yeah, so I think we were planning for Bear to explain her posterior here.
In the case of the summer statistic analysis, we again use left field to produce our galaxy density field, but as opposed to field level inference, where we are using the entire density field for inference, we compress it to power spectrum by spectrum. And how we get to the posterior of our cosmological bias and noise parameters is through simulation-based inference. And the idea here is that instead of you assuming an explicit likelihood, for example, Gaussian or any actual analytical form, you can use neurodensity estimators to find this posterior without relying on any analytical form for the likelihood. This is just an alternative inference method where you relax the Gaussian assumption on the likelihood for the power spectrum by spectrum. And then using this implicit likelihood, you can obtain at the end the posterior of your cosmological bias and noise parameters. And of course, because we are not doing field level inference, we are not actually obtaining likelihood at the level of the initial conditions, which is S hat in this case. It's just for our power spectrum by spectrum, given our parameters of interest. Yeah, this is just an illustration if you were a bit lost with the number of parameters that we have. This is just a recap. So to begin, we have a cosmological parameter that we denote by alpha. This is basically the ratio of sigma 8 inferred to sigma 8 true. And this should be 1 if you have unbiased inference. And our set of VOs are our bias parameters. Our set of sigma Fs are our stochastic parameters. And here S hat is the actual initial conditions of the universe that you have to marginalize over in the case of field level inference. Now we are going to understand how simulation-based inference works in practice for us to obtain the posterior of our cosmological parameters given the measured power spectrum and bispectrum. So here I will start from a very general pipeline framework. So let's say we have some parameters that we draw from some prior. We have a simulator that generates samples of, let's say, our observed data. And we can compress the samples to some summary statistics. In our case, it will be the power spectrum by spectrum, but here again, I'm being very general. And we do this n sim times. So we have n sim the number of simulations that we do that, so that we have a set of parameters that we draw from the prior and corresponding summary statistics that were generated from our simulator. And the question is how we get from the samples to our posterior, that is what we want at the end. So let's say that our parameters are actually one-dimensional. We just have one parameter. And let's say that our data vector of summary statistics is also one-dimensional. And let's say that here in this plot, we simulated n sim times this x given thetas. And we can see here this beautiful scatter here. And I just want to say that what we are doing here are not summary statistic emulators. Here is just a comment for the experts, because sometimes we hear summary statistics and machine learning. And the idea here is that for emulators, you would actually define a model of the mean of your summary statistics given theta, and you would input this for a likelihood, for example, to do MCMC. And as opposed to that, what we're actually doing is, if you want, emulating the entire density distribution itself. So we have actually a model for the probability of, let's say, theta given x. And this is what we call neural posterior estimation. So we use a neural network to find a model of the condition of theta given x, given the points that we have from our simulator, so that we can evaluate and sample from any of these points here. And if you notice, this is actually the probability of theta given x, so for any theta and in any x. And what we are interested in is actually the posterior, which is evaluated at a specific observed data that we measure, for example, from your galaxy density field that you see in the sky. So what we do is that we take a slice of our condition distribution. So here, for example, let's say that your observed summary statistics is that one. When you take a slice of this conditional that you fitted, you have your posterior of theta given your observed summary statistics x naught. And I'm not going to go into much detail, but how we do that is using a deep learning technique called normalizing flows. And this is a very, very useful technique. It's used to basically model any density distribution that we have. And of course, this is very important for us doing inference, because we are usually interested in posteriors or likelihoods that can have some complex distribution that we don't know how to sample or evaluate it. So what we do is just to find a transformation or a sequence of transformations from our complex distribution to a Gaussian distribution. And how we do that, we do this with neural networks. And then from the Gaussian distribution, we know how to sample and how to evaluate this density. And here's just a diagram showing the, for example, 2-moon distribution, which is a very complicated distribution, and how it can be slowly deformed into a Gaussian distribution, which is the one that we start from. And that's basically the idea. So just to wrap up, we had this one-dimensional example of parameters and data vector. So here, actually, in our case, the data vector is the combination of power spectrum by spectrum measured in NSIM simulations. And we basically train a normalizing flow to have the condition of theta given x. And here is like our implicit likelihood, which basically tells us that we are taking the slice of this model that we fitted at the observed power spectrum by spectrum. So this is again the intuition of taking the slice of the conditional distribution that we found a model for. And here is just putting everything together to conclude. So we have theta, our cosmological bias and noise parameters. We draw it from the prior. We evolved them with left field to obtain our galaxy density samples. And we compress it to the power spectrum by spectrum. And we do that NSIM times. And from these samples, we can do a neural density estimator. And then we can take a slice of this neural density estimator at some observed power spectrum by spectrum to then obtain the posterior of our cosmological parameters. And here, the observed data that we use is 2 tracer samples. So we take halos from 2 different n-body simulations and also from 2 different redshifts to show that actually our results are robust across different tracer samples.
Maybe I've just misunderstood something, but how can you get away with only using the power spectrum and bispectrum?
Here we're just using the 2 and 3 point correlation function, but of course you could also measure the 4 point, the 5 point, and so on. And one of the biggest problems with that is that it becomes increasingly more complicated first to measure these endpoint functions and also to estimate if you're doing usual analysis, estimate the covariance of these endpoint functions. And also you need to introduce more nuisance parameters, which are the bias and noise parameters. So it becomes very complicated. What we want to do at the end is really field level inference, which is taking everything at once.
And is that the point that you're about to show on the next slide, that this is not as good as field-based?
Yeah, so part of this confusion, I think, is because of me when I introduced this work. So the point of this work is like standard, like state-of-the-art analysis currently is basically analyzing a combination of power spectrum and bispectrum. So that's exactly what we want to compare with. We want to compare the constraints you get from field-level inference with the state-of-the-art, which is power spectrum plus bispectrum. I don't know if this goes into the final video, but I think one thing that was too modest to mention is like standard analysis of power spectrum plus bispectrum always assume like a Gaussian likelihood with, Gaussian covariance. And what Bear has here is basically a way to move away or move beyond that. So basically now you don't have to assume explicitly a Gaussian likelihood, and then your covariance doesn't necessarily have to be a Gaussian covariance also.
So when you say people normally assume a Gaussian covariance, you mean like between the power spectrum at one value of delta and the bispectrum at another value of delta that they're assuming?
No, for the power spectrum and bispectrum separately.
You can actually include cross correlation between the power spectrum and bispectrum. People have done that. You can also include a cross correlation between different k-beams. But I think what is most important here is that you're not only taking into account the covariance, but also all the higher order moments of the distribution.
So you're being extremely fair in the comparison on the next slide, right? That you're saying this isn't what people are doing, but it's the best that they could do if they were using the power spectrum and bispectrum. So your following contours are even better than what people are actually likely to get unless they do this. Is that also fair to say?
Yeah, Bear can comment on this, but I wouldn't say this is better than what people are doing. But I would just say that this is in principle what you should do. I mean, there's no proof that ignoring, the non-Gaussian contribution to the covariance, or assuming a Gaussian like will significantly bias your results or your constraints. But I think in principle, this is what you should do.
Yeah, we have shown in a previous paper that actually assuming a Gaussian likelihood or relaxing this assumption by using simulation-based inference for the power spectrum by spectrum doesn't make much difference on the large scales. But of course, this depends on the scale cuts you're taking, the cosmological parameter you're looking at, the redshift, and so on.
Yes. So again, this is the results for a simulation at where we identified halos at redshift 0.5. Again, the volume or the tracer density, or rather also the effective volume, closely related to like the LRG samples by DESY Gear 1, I would say. And the scale cuts here are very modest, only 0.1 to 0.12 H over megaparsec. Again, yellow is the power spectrum plus bispectrum constraint from Bear, and then the blue is field level inference from me. So you can see the improvement factor is shown on the top right corners, 3 to 5 depending on the scale cuts. It is expected that the improvement factor increases with scale cuts, because as you increase the scale cuts of your analysis, you in principle have more access to the nonlinear higher order information in your data. What is also very promising that the two analyses provide a completely consistent posteriors, and I think this highlights the consistency in the forward model and um, and how the inference are set up for this apple-to-apple comparison.
Is it right to interpret from this that the simulation-based inference has like a half sigma bias at 0.12 scale cut? Is that?
Yes, there is a slight bias, and this is mainly, we think that this is due to model mismatch, because there is a subtlety that we didn't comment in much detail, but the field level inference assumes Gaussian stochasticity, and the bispectrum of galaxies is known to have some sort of non-Gaussian stochasticity. For the experts, basically the term that goes, it's like the shot noise for the bispectrum and some other density dependent noise. And yeah, basically when you include that, you see that the SPI constraints are unbiased, because basically you are including also the stochastic contributions to the bispectrum. It's in the last plot of the appendix of the paper. Very technical, sorry.
Yeah, the reason we wanted to have the power spectrum plus bispectrum inference with Gaussian stochasticity or Gaussian shot noise is because we want to have an apple to apple comparison. Otherwise, we would have to include this non-Gaussian contribution that Bear was just referring to. However, including that will just inflate the power spectrum plus bispectrum inference. So the improvement factors and the conclusions we are showing here are, in some sense, conservative, I would say. Yeah, and then as a next step, we just grabbed a publicly available simulation of the shelf, and then took the halos in that simulation, in this case from redshift of 1. And then again, we see this kind of not exactly the same number, but similar trends, and roughly similar numbers in terms of improvement factor going from power spectrum plus bispectrum to field level constraints. The way I would read these plots is basically us saying, rather than like as an alternative to pushing our analysis of Gaussian clustering to smaller and smaller scales, but keep using the power spectrum, we can also stay on quasi-linear scales where we have rigorous control on the systematics, but instead explore another dimension, which is expanding the data vector, expanding what we actually model and infer, so that we have more access to information and we have better constraints.
Cool. That's very impressive that we can get such an improvement using field level inference. So where to next? Should we anticipate that by the end of the year or next year that there's a DESI year one data result using field level inference, constraint on sigma 8 and various other cosmological parameters, or what is coming next?
Yeah. So as a next step of this study, of course, we want to make connection to observations. Ultimately, what I showed here, why is a non-trivial problem where we performed and achieved unbiased inference on sigma 8 on nonlinear Bayes tracers, namely dark matter halos from simulations. To really connect to observations, we have to work a bit more. We have to include more observational effects, for example, redshift phase distortion, survey geometry, selection function, and all that. And then also we showed results where we only vary sigma 8, the amplitude of matter fluctuations. But in the real case scenarios, you also have to vary other cosmological parameters as well. For example, omega m or h, Hubble parameter, matter density parameter. And then also, I guess at some point you also want to relax the assumption about lambda CDM or your inflationary model, so to speak. Yeah, so those are the next steps that we are very excited about. Also, of course, there's a question about where is this extra information come from? And I think the next step for us, especially for Bayer, would be to explore, higher order statistics, and again repeat the comparison between field level inference and even higher order statistics.
Well, I think as Bear kind of responded to one of my earlier questions, it becomes trickier and trickier, right? Like if you include the trispectrum, that's computationally a nightmare, and then so if you want to go beyond that, it's probably impossible, and then so you have to use other nonlinear summary statistics, I guess, like voids or density split statistics or.
So one of the biggest problems with the trispectrum is the covariance. And in the SPI approach, we don't have to explicitly model the covariance. Given that we simulate the galaxy density field, we can, of course, just also measure the trispectrum there. And but on the other hand, you have more bias and noise parameters, but we know how to include them also. But of course, it becomes more and more, your data vector becomes huge, and this is usually a problem for simulation-based inference. So you have to think of smart ways of doing that.
These steps to connect to observations are of course non-trivial, especially when you work at the field level. I mean, one major challenge is a lot of systematics and corrections in galaxy surveys are currently performed at the level of 2-point statistics, not even 3 points, right? So, for example, when we compute these galaxy weights, for example, they are supposed to, only have you correct for the 2-point statistics. So, I mean, nobody tested these for 3 points or at field level. So a lot of developments and tests and validations have to happen before we reach that level. But I think ultimately, I would say the promise of field level is that in principle, if you can achieve field level inference, you don't need to do anything else. I think in principle it's optimal, and you use all the information you have.
And can we use field level inference on some slightly older data that maybe is less sensitive and needs fewer tests to?
Yeah. So I think one perfect candidate would be the BOSS gases, in particular the CMAS sample, for example, because we know the clustering statistics on systematics of the CMAS gases very well. So they will be a very good cross check before you open up the Pandora box and apply this to their Z gases.
So should we anticipate cosmological parameter constraints on BOSS data using field level inference sometime in the next few years?
Yeah, next few years, definitely, yes. We all work on that, and that's what we're trying to highlight here with the LabsField logo. So it's actually a very active group, close-knit people working on that.
Cool. So seems very exciting to watch the space and see, as you said, Min, the best that can be done. And I guess it makes it harder to do, but once it's done, it is the best that can be done. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the rest of the community?
Right. So I'm obviously biased, but to me, at the moment in the field, I feel like the effort to go beyond 2-point statistic is certainly underappreciated. I think part of the reason is because the 2-point statistics, or not even 2 points, but just for example, some features in the power spectrum, like the BAO feature, has been so robust and has served us so well that people tend to overlook these two-point statistics or beyond 2-point statistics. However, there's also ongoing within the small community of beyond 2-point statistics. There has been a lot of efforts trying to bring these 2-point statistics to the level, the same maturity level of these 2-point statistics. And one of such efforts, community efforts, is the Beyond 2-Point Mock Data Challenge that is hopefully coming to the archive next month. Yeah, so I'm very excited about this data challenge because it's a community effort where 7 international teams come together to first test and validate our statistics and methods, but also to learn more about the other statistics. So for me, it has been a pleasure because I was able to work with so many people caring about the same thing, and also I learned a lot more about parallel efforts to go beyond 2-point statistics.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. Click like to help with YouTube algorithms, both for the channel and for yourself, because YouTube will know to recommend more stuff like this to you. And share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, why not check out Min's previous talk on the channel on a completely different topic, but just as interesting. It should be on the screen somewhere at the moment. And thanks, Min and Bea, for the great talk.
Thank you.
Thank you.